We're going to be starting our oxidation reduction topic today, and we're going to actually start with some experiments. One of the key things you need to be able to do in your internal assessment is look at some experiments and to work out what species, so which ions or molecules or elements are present at the start, look at what changes and determine what was made. That's your achievement criteria. From that you then have to be able to justify that it's redox by looking at electron transfer. And the way that we do that is using things called oxidation numbers and what are called half equations, which show when electrons are gained or lost. But before we can even start, we really need to know some observations. So using this book here, your beginning chemistry, we're going to go to page 56, and on page 56 is a really good table. That table has got all the species that you need to know for this internal assessment. We're going to look at some of the reactions of some of those in class today. So, if you need to refer to how I made certain conclusions during this experiment, refer to page 56 in beginning chemistry, because it will actually have those for you. So the first one we're going to do is a really simple one, and it's just where I'm going to have some sulfuric acid and my boiling tube here, and I'm going to add some iron powder to it. Now I'm going to heat this up a little bit just with my hands, because it doesn't always start straight away. So I'm just going to give it a little bit of heat from my hands. And we can start to see a few bubbles forming on the surface. So I'm just going to leave that for a wee while. I'm going to leave that for a while just to confirm that it is going to react. We can possibly in the video see a few bubbles forming down here. While we wait, though, I'm going to set up the next one. My next experiment is going to be looking at a chemical called iron 2 sulfate. So iron can exist in iron ions can exist in two forms, either iron 2 plus or iron 3 plus. This is iron 2 plus. And it's a very, very pale green. If we put something like sodium hydroxide in there, it'll make a green precipitate. So we can see it more clearly there. Alright, so if you ever need to confirm that iron 2 is present, you just add some sodium hydroxide and it makes a green precipitate. What I'm going to add to this is a little bit of sulfuric acid, because we want this reaction to be acidic. So again, some sulfuric acid. You seem to have pretty bucket chemistry type stuff here. It's a bit rushed. And then we're going to add a few drops of potassium permanganate. Now it's hard to see in the bottle here, but potassium permanganate is purple or a very dark pink colour. So I'm going to actually make it sit on the top there so you can see it falling in. When it hits the other solution though, you'll see the colour disappears. But you could argue that's because it's being diluted, and actually really we just can't see the colour. So I'm going to add a little bit more. So it's sitting there. And again, if I shake it, it disappears. So it's taking this permanganate and it's changing it. It's got a chemical reaction. Now if I look at page 56, I see that the thing that is next to permanganate is manganese. Well, actually it probably says manganese 2, which is Mn2+. So I know that permanganate is turning into the colourless manganese 2 ion. The iron in here, the iron 2+, is also changing. But iron 2 is quite special. It can either turn into iron metal, and maybe there is some iron metal in there, the particles are just too small for us to see, or it turns into iron 3+. Well, we might remember from earlier in the year we had a test for checking if iron 3+ was present, and it was this stuff called potassium thiocyanate. And it makes a complex ion with iron 3, but not with iron 2. And the colour of that complex is blood red. So we know that the iron 2 has turned into iron 3 because of this blood red complex being formed. Okay. Now let's go back to my good friend the iron and the acid. And you can see it's bubbling a lot more now. Just took a little bit of time to get started. Okay. So what I want to do is check what that's turning into, because it could be turning into iron 2+, or it could be turning all the way into iron 3+. Now, you might remember I said that iron 2+ would make a green precipitate with sodium hydroxide. Well, iron 3+ will make basically rust if I put sodium hydroxide with it. So, we're going to add sodium hydroxide to a little sample I've taken out of here. So I've taken some of the solution out and put it in here. I'm going to check that to see if it's going to go like rust or if it's going to go green. So here's my sodium hydroxide. And it's gone green. So that means the iron metal has turned into iron 2+. Because it was sulfuric acid I made, it was probably iron sulfate, iron 2 sulfate that I made in there. Alright. So, we know that we've had reactions in these. We're going to prove shortly that they are oxidation reduction. There's one more I want to do just to show you. Now again, remember any of these pairs that you're not sure of where I'm getting this information from, page 56 will have that. The last of these is I'm going to take that iron 2 sulfate again, and I'm going to acidify it again. You'll find that most reactions occur under acidic conditions this year. All right. Next year you'll play with some that are neutral and alkaline, but this year I'm going to take a little bit of our iron 2 sulfate again. I'm going to acidify it with sulfuric acid again. And then I'm going to add this orange stuff called potassium dichromate. Now, this has got a nice skull and crossbones for a reason. It's got a form of chromium called chromium 6 or hexavalent chromium. If any of you have seen the film Erin Brockovich, the evil company, or company that's made out to be evil, it's talking about how chromium is actually really good for us and we need it in our diet and all that sort of thing, and so it being in the soil is not a problem. And someone points out that actually that's chromium 3. Hexavalent chromium has totally the opposite effect on our body. It's actually really nasty and can cause things like cancer and other problems. If it's ingested, it can do real damage to you. So we don't want this inside us. It's okay on our skin, as long as you wash it off relatively soon, but you don't want this inside you. So if it does get on your skin, any of these reagents actually gets on your skin, wash it off, because they tend to do a bit of damage inside you. Okay, so we're going to add this dichromate here, which you'll see is orange. It's almost a bit of a yellow colour, and it's starting to go a green colour there. Okay, and the fact that it's green is because we've sort of got the blue chromium 3 mixed in with the remainder of the orange from that. Okay, so it's a bit of a yellowy green. I'm going to find something white to put behind that to show that it's not yellow. Okay, it's got a bit of a green tinge to it. Okay, so in that we can see that in our table on page 56 we can see that dichromate Cr2O7 2 negative is paired up with chromium 3, which is indeed, it should say green or blue-green. Okay, so how do we prove that these are oxidation reduction? Well, I'm going to do that in just one moment. So in our reactions we've just done, we have been able to identify some of the species involved. In the first one, we had some iron, such as Fe, and we added that iron to some sulfuric acid. Now, all acids, whether it's sulfuric, hydrochloric, nitric, whatever, the important thing is that they have hydrogen ions available for reacting. The exception there can be nitric when it's concentrated. It also provides nitrates, which can undergo an oxidation reduction reaction. Okay, but in this case, iron plus sulfuric acid, it's the hydrogen ions that matter. So I'm actually not going to go Fe plus H plus. I'm creating what are called half equations. Half equations show me that electrons are being transferred, which is the definition of oxidation reduction. In oxidation, electrons are being lost. You might hear a little phrase called Leo goes Ger. LEO, losing electrons oxidation. Ger, G-E-R, not G-R-R, is gains electrons reduction. So we're going to be able to find out, we're doing half equations, which one's gaining electrons, so it has electrons as a reactant, which one is losing electrons, so electrons are products. We then did a little test on the resulting solution and found that it made iron 2. So the Fe was being turned into Fe2+. My observation there was that when I took a sample of my resultant solution and I added some sodium hydroxide, we got this green colour here. All right, and that tells us that that has got iron 2 hydroxide in it. All right. If it had gone to iron 3, it would have gone the colour of rust. Right, well, if I look at that top equation, it's nearly actually balanced. There's one iron on each side. But what's not balanced are the charges, and charges are just as important as everything else. So what I'm going to do is I'm going to get both sides to have the same charge by transferring electrons. The charge on this side is 0, so no charge at all. Charge on this side is positive 2, so I need to drop this one by 2 to get it to 0 as well. So I add 2 electrons. So we're actually putting electrons in as if they're a reactant or a product, in this case product. So in this case, it's a product, so they're being lost, so therefore it's oxidation. Another way we can tell is a thing called oxidation numbers, which you'll learn about later. All elements have an oxidation number of 0, because they've got no charge, basically. They've got all their electrons. This has got an oxidation number of 0, and this one here has actually lost 2 electrons, so it's got an oxidation number of positive 2. If the oxidation number increases, we call it oxidation as well. Okay, the other observation in my test tube, which is still going pretty well there, is bubbles. Now, I could actually confirm which gas is being formed, but knowing what's in there, I can make that inference a lot more easily. I can also use page 56 to see that H plus matches up with H2. So I know that the other side of this arrow is going to be H2. Well, that's not balanced because there's 1 hydrogen here and 2 hydrogens here. So I come back here to have another H plus. Well, if I have H plus plus H plus, that's the same as writing this. And again, I have my charge problem. This side's got a charge now of 2 times positive 1, so plus 2. And this one's got a charge of 0, because it's a molecule. So I need 2 electrons on this side. They are reactants, so therefore they're being gained, so it is reduction. Using my oxidation number idea, this one is plus 1, so you might be starting to see how I'm getting these little rules here. And this one is 0. The oxidation number is being reduced, hence the word reduction. Okay, my next trick is to put the two together. Well, if anything appears on the left-hand side as a reactant and as a product, you can cancel it out, so long as they're in the same ratio. I have 2 electrons here and 2 electrons here, so actually I can get rid of them. I just need to add these together. So the final equation will be Fe plus 2H plus goes to Fe2 plus plus H2. Just check that it's balanced. 1 ion on each side, 2 H's on each side. This side has got a charge of plus 2, this side's got a charge of plus 2. Everything's balanced. Okay, my next reaction was a little bit trickier to balance. So, bear with me on this. We had iron 2 sulfate. Now, sulfates can also undergo oxidation reduction, but we proved that that was turning into iron 3. So, we can do our pair for that one. Fe2 plus, which was our green colour. Fe3 plus, which we couldn't actually see because it was so dilute, but we could prove its presence using potassium thiocyanate. So that's our one there. And again, if we have a look at it, the ions are balanced, but the charge is not. So for this, I need another electron. So this is my oxidation one. Just so we can look at oxidation numbers. Guess what number that one is? Plus 2. Cool. Guess what number this one is? Plus 3. So we're starting to see a little bit of a pattern. Again, the number gets bigger, so it's oxidation. Right, the next one's a bit trickier, so bear with me while I teach you how to do this one. And the other one, the other half of this, we had permanganate, MnO4 negative. Now, I'm not going to show you how to do it yet, but I'm going to ask you to believe me that its oxidation number for manganese, I'm not going to worry about the oxygen, manganese is plus 7. Okay? I'm just going to ask you to believe me on this one. I'll show you how to do that at a later date. Alright? It becomes, what's the pair on page 56 for permanganate? Mn2 plus. Great. Like a smaller arrow. I think we're going to get a bit busy in here. Guess what its oxidation number is? Plus 2. Cool. Now they're not always positive. Sometimes oxidation numbers are negative. The oxygens in here have got an oxidation number of negative 2. Alright? And they will have on the other side too, by the way. The oxygens are not involved in the oxidation reduction. This one's a lot harder to balance. So here's how I balance a half equation that isn't so easy as just doubling things up and adding electrons. My first step is to go, in this case, are the manganeses balanced? Yes, okay, so I don't do anything then. But there's oxygens here and there's no oxygens here. Well, I didn't see any oxygen gas being made or anything like that, because they make bubbles. What I did notice is that it's a solution. And solutions have got, what? What are they dissolved in? Water. Okay. So if I put water over here, I don't actually affect my reaction at all. I'm just saying, oh, there's some water there. How many waters do you think I need to put over there? 2?
4.
I've got 4 oxygens, so 4 of them. Great. So I'm going to go plus 4 H2O. What I've now done though is created another problem for myself. I've now put hydrogen atoms in there, 8 of them. But what did I add before I added the... Sorry, grabbed the wrong one there, didn't I? Oh no. What did I add before I added the permanganate? Sulfuric acid. Which ion do acids provide?
Hydrogen.
Hydrogen. So I can put those over here, and I'm allowed to. 4 times 2 is 8. 8 hydrogen atoms. Right, now, here's the tricky bit. I have to work out the charge on each side to see how many electrons I need to use. Alright? I've got, what is my overall charge on the reactant side? Careful, you got that one there. So 8 times 1 is 8, minus 1 is 7. That's interesting. And the, over here?
2.
Plus 2. Same again. So how many electrons do I need to put on the reactant side to get it down to 2? 5. Awesome. That's the second hardest half equation you're going to meet this year. Alright? The rest are pretty easy. Now, putting them together is a little bit trickier. So, here's how we do it. Well, notice that you've got 5 electrons in this one, but only 1 of this. So that would still leave 4 electrons here if I was just to put those together, wouldn't it? But those electrons have to come from somewhere, and that somewhere has to be iron 2+. So for every one of these reacting, you actually need 5 of those. Which means it makes 5 of those and releases 5 electrons. So we're going to have 5 of this entire equation. So the way that I normally do it is I keep my arrows lined up because I just like to be a little bit organised like that. Maybe I'm a little bit OCD. So I get my 5 Fe 2+ here. I put my 5 Fe 3+ here. Then I put the rest in. Remember, the electrons disappear because they're reactants and products, so they're gone. So I put my plus MnO4- plus 8H+. So I've got all of those in. That's crossed out, so that's good. That's crossed out as well. Okay, and then my plus Mn2+ plus 4H2O. Fun part. Check if it's balanced. The iron atoms, iron ions clearly are, aren't they? 5 and 5. The manganeses are 1 and 1. I've got 4 oxygens. 4 times 1 is 4. 8 hydrogens. 4 times 2 is 8. But I always like to check the charges as well. 5 times 2 is 10. Plus 8 times 1 is 18. Minus 1 is 17. 5 times 3,
13.
plus 2,
17.
so the charges are balanced as well. Alright? If the charges aren't balanced, it means you've made a mistake with how many times you've multiplied one of the equations. Alright? Now look, the last one I'm not going to do on the board for you because I'd like you to have a go at it, where we've got iron 2 sulfate and potassium dichromate, which was not that one. Where have I put it? I got rid of it already. There we are, where it made that green colour, so it's making chromium 3. Alright? My hint to you there is make sure you balance the chromiums first in that one's half equation. Alright? So that one you'll do yourselves. I'll leave that up on the board so that you can have a look.